In this video, we are going to look at Unit 7, Lesson 13, which is using radians. By the end of this lesson, you're going to be able to find the area of a sector with a given radius and its central angle given to you in radians. This starts on page 234 with this question, what fraction? So given that the radius of a circle is 24 inches and the central angle is pi over 3 radians, determine what fraction of the circle is represented and what's the area. And then you can come back to the video. So if we've got pi over 3 radians, that means that the top part of the circle is being split into 3 equal parts. So we would have one of those, and that's going to split it into 6 equal parts. So if we're going to split the top into 3 equal parts, that means that this whole circle would be split into 6 equal parts. And we would have 1/6 of the circle. So finding the area, you've got the radius is 24. So remember, we square the radius and multiply by pi. And then in this case, we only have 1/6, so we'll divide that by 6 as well. So 24 squared is 576. So we have 576 pi for the area of the whole circle. Divide that by 6. And we get 96 pi inches, whoops, not 9, 96 pi inches squared for the area of that sector. All right, so I want you to sit and think for a minute about how you would find the area of each of these 2 sectors. I don't need you to actually calculate the area of each sector, but I would like for you to talk through how you would go about it. So how would we find the area of each of these sectors? Once you've talked it through, come back to the video. So in each case, we've just got a part of the circle, right? And so we would want to figure out the portion. So what fraction do we have? Okay, or what portion do we have? Which is going to change depending on these circles, right? When we're figuring out this one, because this one's measured in degrees, okay, remember portion is part out of whole. So then the whole thing here, okay, the whole central angle would be 360 degrees in this one versus the whole central angle when we're measuring in radians, the whole thing is 2 pi. So when we're determining what portion, here we would be looking at maybe 36 divided by 360. Or if you wanted to figure out how many equal slices went in there, you could do 360 divided by 36 and take one of those parts. Versus this one, you'd be wanting to figure out what fraction pi over 5 is out of the whole circle, and you could certainly do it this way. You could think about splitting the, circle up. So if we took pi, this part's going to be split into 5 equal parts, so then this one, and get 1/10 of the circle that way. Could also do 2 pi divided by pi over 5. But then you're getting into fractions of fractions, so maybe it's just looking at how many times this fits in the circle by just looking at the number of parts that you're splitting it into. And then you would multiply those portions by the total area. Okay, so once you figure out what portion, you'd be doing the portion times the total area. Or if you wanted, you could take the total area and divide it by the number of parts. Okay, you could certainly do total area divided by number of parts as well. So on page 234, we talk about Lynn and Elena are trying to find the area of this shaded picture in the image. So Lynn says, we've found sector areas when the central angle is given in degrees, but here it's in radians. Should I start by finding the area of the full circle? Elena says, I saw someone using the formula 1/2 times the radius squared times theta, where theta was in radians and r is the radius, but I don't know where it came from. So here's that formula that Elena said she saw somebody working with. So in your book on page 234, we kind of talked about the differences in kind of attacking degree versus radian. So let's look at now explaining why the formula that Elena saw works. So see if you can think of why it works. Try it and then come back to the video and I'll talk through it. All right, so if we just thought about in general, and not this problem, but if we just thought about finding area of any circle, right? We just said we would do the portion times the area. And that would give us our sector area. So I'm just going to call that S. And so what portion of a circle do we have in radians? So no matter what that central angle is, we're going to compare that to 2 pi, the whole thing. So this will give us our portion. And again, we're doing it in general, not for this given angle. So if we just didn't know that, then times it by the area of any circle. And the area for any circle is pi times the radius squared. So if we simplified this formula, right, we could cancel out these pi's because pi divided by pi is always going to be 1. So then we're seeing that we'd have theta times r squared on the top, and we'd have divided by 2 on the bottom. And that means we have a 1 up here. So we could kind of rewrite this as a fraction, 1/2 times theta times the radius squared. And we could certainly move the radius in front here since multiplication is commutative. We can change the order. And we could do 1/2 times the radius squared times the central angle in radians. So that is why that formula is going to work anytime. So now use that formula to find the area of this sector. So area of this sector is going to be 1/2 times the radius squared, which the radius in this case is 12, and then times the central angle in radians, which is 3 pi over 4. So we're going to get 1/2 times 144 times that 3 pi over 4. So you can do this in a couple of different ways. If you want to do half of 144, I'm going to do that so that I can reduce my numbers. So half of 144 is 72 times 3 pi over 4. And then 72 divides by 4. And 72 divided by 4 is 18. So if I take and divide that, I'm going to get 18 times 3 pi. And then 18 times 3 is 54. So we get 54 pi units squared for this area. All right, go ahead and take a look at these questions, think through them first, and then come back to the video and we'll talk about them. So would this formula work if the angle was measured in degrees? And the answer to that is no, because where we ended up getting this formula, if you remember, was by taking theta over 2 pi times the area, pi times the radius squared. And so this whole part was coming from radians. So if we wanted to do it for degrees, we certainly could substitute in that the whole, when we're comparing a degree angle to the whole circle, then this should be a 360 times pi times the radius squared. So when we're doing part of our angle out of 360, if it's measured in degrees, or part of it out of 2 pi when it's measured in radians. This one just wouldn't have anything simplify out like the radians did. Is this formula the only way to find area of a sector when it's measured in radians? And that is no. You could certainly look at what portion of the circle you had. So when we were talking about that first one and we said if this was a pi over 5 angle, then we would know that we have 10 equal parts in the circle, 5 on top and 5 on bottom. So we could take the total area and divide it by 10. Or you can use this formula as well. But either way, there's multiple ways to do it. So what are the advantages of using the formula to calculate the area of the sector? So it's a pretty simple formula, okay? 1/2 times the radius squared times theta. There's not much complicated stuff in it, so it's a little bit simple. But you also have to remember the formula in order to be able to use it. So if you don't remember that formula, you're not going to be able to use it. And it might be easy to just be doing the fractional portion of the circle that way. All right, then let's take a look at this next activity here. So I just took a map of downtown St. Paul, just kind of a simplified version of downtown St. Paul where 35E comes into downtown. And I blew up that chunk. So here's 35E, and we've got the 6th Street exit and the Kellogg Boulevard exit. And this is just to give you some kind of perspective on what we're looking at here. And then I have Wabasha Street highlighted. And so you kind of see like you could exit on 6th Street and you could get over to Wabasha by following kind of this arc. And same with Kellogg. You could exit on Kellogg and then you get over to Wabasha. Okay, it's more on this arc, right? Okay, so in order to get to Wabasha, you could go that way. You could also go directly as 35E follows to get there. All right, so then let's take a look at page 235, and we have a very simplified version of a map here of the city of Riverside. And Riverside has these 2 highways that are connected, so connecting to the town hall at point T. So here's the first highway, here's the second highway. Okay, and they have all these exits and these curved roads that connect those 2 highways. And what our goal here is going to, is looking at the radius from how far the road is from Town Hall and then how long the road is. So they give you both of those measures. So we see that exit A is 2 miles from T and that the curve that goes with that road is 3 miles to get to the next highway. Then T to point B is 6 miles. And then the road that connects the 2 highways from that exit is 9 miles. And so what we want to do is get a table that connects these. Okay, so I just drew out a table here. So go ahead and you can create a table. So let me get you started and then I'll let you pause to do a little bit of this. But remember the radius, so we're looking at this. So the radius is how far is the exit from Town Hall. So this one is 2 miles from Town Hall. And then what's the curve that goes with it? And in this case, that's 3. And then the other one that we just talked about was from T to exit B. That's 6 miles, 2 plus 4. So we get 6 miles here. And then the radius of that road, the arc length of that road is 9 miles. So go ahead and finish those last 2 and then draw the dots. And then you can come back. All right, then to point C would be 11 miles. 2 plus 4 is 6, plus 5 is 11. And then the arc would be 16.5. And then to D would be 14 miles, and then the arc being 21. So 14 for the radius, the arc is 21. So now we want to plot these points, and so go ahead. So we need to get up to an arc length of 21. So I know that I need this axis to reach to 21. And so if I count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I'm going to need to count by 2s. So 2, 4, 6, 8, I'm just going to mark this one at 10. and then 12, 14, 16, 18. This one's going to be 20. And then I'm just going to do the same thing this way as well because I need to get to 14. And so this is only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 again. So I'm going to count by twos and label this at 10 and this at 20 miles. So then plot these points. And so our first one was 2. Okay, so 2, 3. So this is 2, 2. So 2, 3 is going to be right in between. Then this one is 6, 9. So 2, 4, 6. 2, 4, 6, 8. So 9 is going to be right in between there. 11. So here's 10. So 11 is going to be halfway. 2, 4, 6, 8, 10, 12, 14, 16 and a half. So just above there. And then the final one was 14. So this is 10, 12, 14, and then 21. So plotted those points. Appears to be a line, so a straight line relationship here. So if we kind of looked at that. So let's write the equation of this line. So for this line, you just need any point that it will go through. Okay, so whatever point you want. And actually in this, we could change these instead of X and Y because our X is actually our R. So instead of X, I'm going to put R. And our Y is our arc length, which we've been calling L. So let's find, you can literally choose any of these 4 points that you want. I'm just going to go with this first one and plug this in. Okay, so I'm going to do R minus 2 and L minus 3. And then you can count the slope. So now we need the rise over run here. So count rise over run. So I'm just going to connect these 2 points here and look at what that is. So let me get these labeled so we can look at them. So this was the 0.23 and this was the 0.69. So this rise is going to be comparing your X coordinate, or sorry, your Y coordinate. So comparing the movement up. So 3 to 9 would be a rise of 6 units. And then this run is going to compare your X's. So how far did we move from 2 to 6 was 4. So then our slope, okay, so then this slope is going to be rise of 6, run of 4, which simplifies to 3/2. So we'll put that in here. And then we have our line. So we have L minus 3 equals 3/2 times R minus 2. And so what does the slope actually mean in this situation? So what does this 3 divided by 2? So you can look at it as 3 over 2 or as 1.5, but what does that slope actually mean? And so if we take a look, it's the arc length or the road length in miles per radius change, right? So it's road, the length of the arc, okay, over the exit change. So for each 1 mile further that the exit is, the road length is 1.5 miles longer. Okay, so as this increases by 1.5, that's for every mile it goes further. And you could look at it also as like for every 3 miles, the road gets, or for every 2 miles longer, the road gets 2 miles longer. The exit 2 miles further, the road gets 3 miles further. So how long would the new road be if the exit is 6 miles past D? So if we added another 6 miles on here, okay, and we put this new exit, what would our new road length be? So if we went 6 miles past here, that would be at 20. Okay, for every 1 mile further, so for every 1 mile further from Town Hall, we add in 1.5 to the arc length, and we just added 6 miles. So if we do 6 times 1.5. Okay, so 6 times 1.5 is 9. So we're going to have to add 9 miles to this road length. So then it's going to be at 30. That's one way to think of it. You can also think of it as how much divided by 20 would equal down to 1.5. And so thinking 30 divided by 20 would equal down to that slope. You could proportion it out as well. So x out of 20, okay, because we know it's 20 miles for the roadway, would equal that slope of 3/2. And then you could cross multiply if you wanted to get 30 that way. All right, so does 1.5 radian measure for the angle in this activity make sense? Because that 1.5 or that slope is our angle measure, right? Because we got this arc measured at 9 and the radius was 6. So when we did 9 divided by 6, we were getting that 1.5. Or when we did 3 divided by 2, we got that 1.5. So arc length divided by radius is our radian measure. So does this make sense? Well, when we think about a circle, okay, and half of a circle, if this is pi, okay, you can split in, so half of, so we think about 3 radians fit in here. We know about 3 radians fit in. So if I split 3 in half, and when we did that string activity, we got 3 radians went to about here. So it would make sense then that 1.5 radians is just under half of pi. Since pi is a little bit more than 3, this is going to be a little bit more than 1.5. Okay, so it's going to be a little bit more than 1.5. So 1.5 being a little bit smaller than a 90-degree angle. Okay, which that's a little bit smaller than 90, so that makes sense. What is the definition of a radian measure, which we just kind of talked about again, but the radian measure is equal to the arc length divided by the radius. Okay, so that's a radian measure. What does this equation represent? And so we see that 360 degrees, we see this. This is circumference formula. And this is a partial degree out of 360. So they're doing a part over 360. So this would be a fraction of a circle, or fraction for a sector, with the central angle in degrees. So if we're looking at part of the whole circle's circumference, we're looking at an arc length formula in degrees for the central angle. So what are the advantages and disadvantages of degree and radians? So radians can kind of simplify out formulas that you're using. But degrees are probably more familiar than radians since you've used them a lot. But radians will get us some easier formulas rather than arc length. We just had to multiply radius times central angle and you get arc length, versus in degrees, you have to do the degree divided by 360 times the circumference. So if you can work with radians, a lot of calculations will be simpler. The radians often do have pi and fractions in them, which might make it more complicated for some, but maybe less complicated for others. And when we know an arc length, so like in this one, we knew the arc length of 9 and we knew the radius of 6, we instantly could come up with the angle of 1.5 in radians. It's more difficult to come up with the angle measure if we wanted it in degrees. All right, so what 2 formulas did we learn today that use radians? So one of those formulas was for area of a sector. So I'm just going to call that S. And so we looked at S equals 1/2 times the radius squared times theta. We also looked at arc length. Okay, so we know that we can get, and I'm just going to write the definition of a radian first. So we had a radian equals arc length divided by the radius. So if we just multiply the radius up, we actually find out that arc length in radians is just radius times the angle. So here are the two formulas, sector area and arc length with radians. And now just, if you're in class, talk to each other about the number of different facts that you can record about radians. If you're at home, you can just think about how many things you know about radians. And then here are a couple things that I think you should highlight in the summary. So this area formula with radians, and then the arc length formula with radians. And then here's the cooldown. So you should hopefully be able to find the area of a sector with a radius of 6 and a central angle of 4 pi over 3. If you need help, be sure that you reach out to your teacher.